So on the M step of the expectation maximization algorithm for restricted Gaussian mixture model, we have to maximize the following expression. So we have to find the maximum of sum with respect to individual objects in our dataset, training objects, of expected values with respect to the variational distributions Q of Ti of the joint log likelihood of xi and ti, given the parameters. And here with the parameters are just mu, so given mu. And maximize this expression with respect to mu. Mu1 to mu number of clusters. So we can maximize this thing explicitly by, finding its derivative and setting it to 0. But recall that on the previous video we maximized the same expression for Gaussian mixture model. So we can now reuse the results from that video in this one. So recall that the optimal parameter for mu number c, for example, was the following one. It was the average with respect to all the data points in our training dataset times the variational distribution Q, so the weights of Ti equals to C, the weights according to the current Gaussian C, times the data points xi, divided by the normalization, so now the sum of all the weights Q of Ti equals to C. And recall that in our particular case, on the E step we are using delta functions instead of the full variational distributions Q. So our Q looks like this. Q of Ti equals to 1 if Ti equals to Ci star, which we have already pre-computed on the E step, and 0 otherwise. So we can continue this expression and simplify it by using this definition of Q of Ti in this particular case. So this thing will be just, again, sum with respect to all the objects, but all the objects that doesn't have Ti equals to Ci star or to C, so they will not contribute to this sum, right? So any object which didn't came from the Gaussian number C, it will have the weight Q being 0, both an numerator and denominator, and so it will not contribute to this sum. And thus we can write down like this. We can say that this thing will be equal to sum with respect to all objects from the Gaussian number C. So all I such that Ci star equals to C. We'll average these data points and divide them by normalization, by the number of such data points. So it's number of I such that Ci star equals to C. And this is exactly the formula for the k-means algorithm on the second substep. So to summarize, we have just proven that the M step of the expectation maximization algorithm applied to this restricted Gaussian mixture model without some parameters, where we leave just the allocations mu of the Gaussian parameters. And if we use the Q, the restricted Q being the delta function from the restricted E step, then on the M step we obtain this kind of formula. So we have to update mu's as being the centers of all the data points assigned to the cluster number C, which is again exactly as we had in k-means. So to summarize, k-means is actually a special case of applying the expectation maximization algorithm to Gaussian mixture model. But first of all, this Gaussian mixture model has to be some kind of restricted one, where we set covariance matrices to be identical and the prior probabilities pi c to be uniform. And we also have to use simplified E-step. So instead of considering the full posterior distributions on the E-step, we're approximating them with the delta function, which kind of makes E-step and M-step faster, but also restrict the flexibility of the model and efficiency of the AM algorithm. But anyway, this kind of restriction still gives you a valid EM algorithm, which still is guaranteed to converge and has nice properties. So it's really cool. We have just took your usual machine learning algorithm for clustering, which is not probabilistic in any case, in any sense, and we showed that it's a special case of the EM algorithm applied to some restricted Gaussian mixture model. So now we can, using this knowledge, we can, for example, change something in k-means, and we know how to adapt the training algorithm to these changes. For example, we can introduce missing data, and this way we can build a missing data k-means without heuristics like setting missing data to 0, but by just extending this restricted EM algorithm and handling this missing data naturally. And actually this kind of trick to simplify the E-step by considering a restricted set of distributions is strongly connected to something called variational inference, which we'll discuss in week 4.